we have a very special one for us here today. But I'll give everybody a few minutes to join here. In the meantime, I will launch. I got some polls going. And sound off in the chat if you have any issue seeing the polls. But yeah, we have a very special deep dive here today. Zach Romer from Empirico is one of our most engaged community members. And chances are, if you asked a question in our community Slack, Zach has answered it for you. And he's been involved with the Dagster project for some time, predating both me and Colton. So I'm really happy that we could get him on and he could take time out of his schedule to show us how he's handling the really insane scale of the data engineering that they're working with over at Empirico. Because personally, I've only ever worked with relatively small data sets, but never in the petabyte scale. So I'm sure there will be a lot of good takeaways for whether you're working with a regular sized data set or a big one out of this. So.
Yep. And as a reminder, this will be recorded. So if you're not able to catch it live, or if you want to share it with some of your coworkers, you'll be able to do that. And then if you have any questions, feel free to ask them in the Q&A section, and Alex and I will field the questions as Zach is presenting.
Awesome. So yeah, we'll give it another minute or so. But yeah, I know here at Dagster, we've had a lot of big updates that have happened over the past few weeks. We've had the enhanced Dagster Plus UI land, which I don't know, it's super beautiful and a really intuitive way for doing those day 2 operations. And then we've also launched Compass, which is in early preview, which is our AI data and analyst chatbot that we really tried to take governance and control at the basis of it. So you can check those out on our YouTube if you haven't seen it yet. But yeah, I think we got enough of an audience here. We can kick it off. Colton and Zach, you want to introduce yourselves?
Sure. Yeah, I'll go ahead and go first and then let Zach take it away. But I'm Colton. I'm a developer advocate here at Dagster Labs. I've helped work on educational content, some of the integrations that you might have used. I'm just super happy to be here alongside Zach as he shares his story with Empirico.
Thanks, Alex and Colton. Also very happy to be here. Appreciate the invite. It's been a long time coming. And yeah, I guess I'll go ahead and get started then. So yeah, a little bit about me. I'm Zach on the Slack channel. If you've been a part of the Slack workspace, like Alex said, there's a fair chance I've answered one of your questions, hopefully correctly. Apologies if not. I've been working as a lead data infrastructure engineer at Empirico since 2021. I primarily focus on helping scientists build applications to solve complex problems with data. I've been working with Dagster for about 3.5 years, since right before the Dagster Plus or Dagster Cloud at the time release. So been working with it with some time, and the framework's come a long ways. It's been a lot of fun to be a part of the community. So just to give a real high level overview of what we're going to be talking about today, I'm going to give a quick intro to Empirico and what we do, as well as how we use genome-wide association studies as kind of a case study in the types of analyses that we perform. Then I'm going to talk about resources, Dagster resources as an infrastructure layer, and dynamic graph-backed assets and how we use them to fan out across large analyses. And then I'll get into a little bit of managed external execution, just how we manage these executions across external cloud platforms and cost observability. And then I've got a little bit of a summary and with some resource links and thanks to everybody. So we'll go ahead and dive into it. So Empirico is a biopharmaceutical startup company. It was started in 2016. What we do is we analyze the world's largest public and private population genetics data sets so that we can find relationships between genetics and disease. The relationships that we discover are used to inform the development of novel medications that are used to treat diseases affecting millions of people. We've been using Dagster since 2021. I think that was right before software-defined assets were released. So I want to talk a little bit about data-driven drug development, which is our bread and butter. So we ingest data from a lot of different sources so that we can build internal data sets that our drug discovery scientists can access and query through internal applications that we build. Dagster plays a really important role in building these data sets. And while generating that data is really only a small part of the drug discovery process, it's a really important foundation for our scientists to build upon. Our scientists have come up with multiple validated drug targets that were found using data that was generated with Dagster, which we're really proud of. Our data infrastructure technology at Empirico is relatively basic, I like to think. We try to be pragmatic in our technology selection while also being open and interested in any new tools that come out as they do. And we primarily use Python tooling. We have a couple different data frame libraries and use depending on the scale and the use case. So we use Pandas and Polars and PySpark. We have some fast API for internal APIs. And then there's a bunch of different bioinformatic libraries and statistic libraries in use. We're heavy users of the Delta format and use Postgres to house operational metadata such as job and result tracking. And then we're also multi-cloud, partly due to obligation, due to this restrictive nature of some of the data sets we leverage, which I'll talk about a little bit here in a moment. So let's talk a little bit about a type of analysis we perform that allows us to get these insights into new drug targets. So this is called a Genome-Wide Association Study, also known as a GWAS. So GWASs allow us to calculate the likelihood that a particular genetic variant contributes to or protects against a particular disease. The basic idea is that if we can determine that a genetic variant found in some people protects against a particular disease, maybe we can create a drug that will replicate that protection in other people who don't have that genetic variant. An example of this in the early 2000s was a variation in a gene called PCSK9 was found by researchers to provide a protective effect against certain forms of hard to treat high cholesterol. And so scientists were able to replicate this effect the variant has in the body by creating novel drugs. And those drugs are currently on the market and regularly prescribed to people with those forms of cholesterol in combination with other treatments. But anyway, the GWAS studies are complex and they rely on a lot of data and complex linear algebra and statistics to measure the likelihood of association between disease and genetic variation. The larger the sample size is, the greater our predictive power, as most statistics are. The genetic data is really big, so a single person can potentially yield hundreds of gigabytes of data and sequence DNA, depending on the type of sequencing that we're doing. Biobanks, which are large collections of samples, they can have hundreds of thousands of these samples. So as a result, when you look at the size of the genome for an individual multiplied by the hundreds of thousands of samples in a biobank, you can easily get into the petabyte scale data. The biobanks are also growing rapidly in the size and number of different institutions. There's a number of biobanks in the next couple of years that are going to be aiming to have millions of samples. So it's a lot of data. The amount of genetic data for analysis has been growing by easily an order of magnitude every couple of years for the last decade. Another thing to point out here is that the data is incredibly sensitive. It's literally a person's DNA. It's probably the most personally identifiable piece of information there is. You can get a new social security number, but you can't get a new genome. That means it's often bound by very special regulations, and the data can only be accessed from highly restrictive, purpose-built cloud platforms where we don't get to choose the infrastructure we have access to. Whether the compute is a VM or some container service, whether it has root access, whether there's inbound or outbound network access, very much depends on the service and the regulations of the country the data is stored in. So a lot of unique challenges in integrating with these services. Here's some quick numbers to give you a sense of the scale we're working at. So the source data, like I said, can be petabytes in size. with individual data sets ranging from just single-digit gigabytes to hundreds of terabytes and hundreds of billions of rows. The biobank scale data requires billions of statistical tests to be performed across tens of thousands of machines running for days or weeks at a time. This results in hundreds of thousands of CPU hours and hundreds of terabytes of RAM being used over the course of a run for our largest analyses. So obviously at this scale, there's a lot of challenges that come into play. Basic GWAS for just a couple diseases can be done in just a Jupyter notebook on a laptop, just tracking the compute jobs manually. But when you're running hundreds or thousands of jobs across thousands of machines in multiple different cloud platforms for potentially weeks at a time, failures can happen for all kinds of reasons. Many of these failures are transient, so things like networking failures, disk failures, spot instance interruptions, things like that. Tracking and categorizing and handling all these failures is not trivial. Just keeping track of all that is very difficult. So measuring and identifying performance issues also gets a lot harder when you have more machines involved. And these analyses can easily cost tens or hundreds of thousands of dollars. And just getting an accurate total cost when you're spanning multiple clouds is very difficult, much less trying to get a cost per job run or per row of output, which is a really nice way of measuring your cost. And this kind of cost observability requires a lot of upfront investment. So Dagster gives us a control plane that we can use to operate these huge analyses at a higher level of abstraction. It gives us a lot of operational metadata that we can use to track and analyze the completion and performance of these analyses. It also gives us layers that the infrastructure team can use to inject tools and functionality into analyses in a way that enables our scientific subject matter experts to focus on the details and logic of their analyses instead of dealing with distributed systems problems. So let's talk a little bit about how we use Dagster to solve these problems. At a high level, we use Dagster in a couple different ways. A lot of our pipelines are kicked off on demand by scientists to answer some sort of research question. So we have an internal web UI that scientists can submit jobs through. Pipeline developers can also submit jobs directly to the Dagster UI when they need to do things more complex or they need to test things. We also have a lot of scheduled asset pipelines that are used primarily for ingesting operational metadata and cost metadata. And then we use a lot of different Dagster abstractions. We're really big fans of assets, of course. Asset checks have been really valuable to us. We like IO managers a lot for how they decouple our storage and our business logic layers. We use factory functions quite a bit, although those aren't necessarily specifically a Dagster abstraction. They help us generate Dagster abstractions. And then we use resources quite heavily. And I'd like to talk a little bit more about resources as they're quite critical to how we operate at scale. Dagster resources provide a really nice way to implement dependency injection in your pipelines. If you need a quick refresher on dependency injection, it's basically just a fancy term for passing some entity or object your code depends on as a parameter to your code. This is useful because it allows you to change the implementation of the object you pass in without changing the implementation of the code that depends on the object, as long as the object implements the same interface. One practical use case for this is swapping in stubbed or mocked resources so that pipelines can be end-to-end unit tested, which is something we do really commonly. To make things just a little more concrete, this example shows an external execution resource being injected into this process batch op. The code of the op itself is not dependent on the implementation of this resource. All it really cares about is that this resource exposes a trigger for execution method, and that method takes two parameters. We could easily call the op with a different resource as long as it exposes the same function with the same number of parameters. We try to use resources to abstract most things that make network calls. So any REST API clients, database clients, work sessions, FTP, SSH, all that stuff. So let's dig into that external execution resource a little bit further, since this is what we'll be looking at throughout other parts of the presentation as well. So this is one of the more widely used and impactful resources that my team has built, and it allows users to execute arbitrary Python code on remote compute platforms. Due to the size of data that we're analyzing, a lot of our pipelines need to execute at least one of their steps on an ephemeral remote cluster of some kind, possibly multiple clusters. This resource allows our pipeline developers to focus on the complexities of modeling relationships between biological entities rather than figuring out how to run their code on distributed systems. They can define their domain logic once in the same repo as their pipeline definitions and run that code reproducibly in one of many remote compute environments. In some cases, we rig up the resource to automatically determine which external platforms to run an analysis on based on the data sets the user wants to analyze. This further removes the need for pipeline operators to know the specifics of the different platforms we interact with. It's hard to overstate the productivity gains when your domain experts can truly focus on the domain while still being able to self-service large-scale pipelines across multiple backends. This resource you see exposes a number of different configurations that allow users to declare strategies for retries, for their cluster configuration, for instance selection, and it also allows automatic tagging that's important for granular cost tracking across platforms. As a general pattern, when we're defining resources in Empirico, we try to isolate our internal logic from the Dagster layer. So in this example, we see that we have this external execution client is where the bulk of our logic actually lives, and then we don't actually pass Dagster specific objects into this class. We just kind of decouple. We use this configuration resource layer to decouple the internal execution client from the resource that we expose to pipelines. So let's talk a bit about how pipelines use this external execution resource. So basically we're getting into fan outs here. So as I said, we're constantly having to fan out data across multiple machines when we run these analyses. The first thing that happens in these processes is that a user provides a selection of dimensions that they want to parallelize across as an input to the job. This is the batch configuration in this case. Then there's a batch calculating step that will take that configuration and, as the name suggests, create batches of configuration that downstream steps are going to operate on. If you're familiar with partitions, data sets like Parquet, you'll see this manifest as multiple partitions being sent to the downstream jobs. Then we have our actual fan out processing step, which uses the configurations that was passed to pull down partitions of the data set into memory to do the processing. Finally, there is an optional post-processing step that can be used for QC, like yielding asset checks or doing some sort of alerting. On the right here, we've got a snapshot of what Dagster shows when you create a dynamic fan out like this. So there's two different actual syntaxes in Dagster that we're combining here in order to make this all work. The first is dynamic graphs, which allows you to define a graph whose structure is not known until runtime. And then we're combining that with graph assets, which makes it easy to turn that graph into an asset. If you're unfamiliar with the syntax for either, I've got some links at the end of my slides you can check out. Every fan out has a starting op that's responsible for generating batches, like I mentioned. This batching logic can be very complex and very granular, so it's usually defined elsewhere as a separate function, continuing on that pattern of isolating internal logic from our Dagster layer. And then that batching logic is also quite specific to the analysis that the pipeline represents. Each of the batches that this generate batches op is going to generate becomes a process batch step downstream of this. So if we yield 10 batches here, we're going to get 10 process batch steps in this part of the pipeline. In this step, we see that we have the execution engine resource being injected here using Dagster's resource injection framework. Once we're going to get into a little more of like how this external execution works in a second here. But just to wrap up the pipeline definition, we finish off with a post-processing step. I left out the details here, but this is where we can collect all the results from those different processing steps, do any QC or alerting we need to do, and then return the final output that we're going to represent as the asset for this pipeline. Down here, you can see where the magic happens with the Dagster syntax, where we call .map and .collect to perform the fan out and then collect the results of that fan out into the list. So let's move on to checking out what a fan out looks like in Dagster. So here we've got a view of what when I run a job that's doing a fan out, what happens. So we yielded 10 steps from the batching op at the start. Each of those became a processing step. It's in our code we saw is going to trigger an external execution. This is just kind of a mocked version of that, so that's why it happens so fast. But once all those finish, we return the results to our post-processing step. We use this pattern to fan out pipelines with hundreds or thousands of individual steps. And like I said, most of those steps are orchestrating an external job. One of the really big benefits we see with using this pattern to orchestrate across these big fan outs on external platforms is that we can collect all the logs in one place. So this view doesn't show it very well, but the Dagster console logs are here. When we're fanning out across external platforms, we actually funnel the logs from all those external executions into the console here. And it gives the pipeline operators a really nice single place where they can view all the logs that are pertinent to their execution, see errors, and not really have to travel to those external job UIs all the time. That greatly reduces context switching and helps developers kind of stay focused on the pipeline and the overall health. We still link out to the external job UIs in the logs so that it's easy for pipeline operators to traverse from this view into more specific views for a specific job when they need to get into deep debugging. So just to summarize what we learned about dynamic graph-backed assets, we found them to be a really great tool for giving us this high-level orchestration observability view when we got to run large amounts of external compute. It gives us a lot of visibility across all those platforms and gives kind of a single pane of glass that our operators can understand pipeline health with. So now that we've talked a little bit about dynamic fanouts, let's dig a little bit further into that external execution resource layer.
Zach, we actually had a few questions, if you don't mind.
Yeah, let's talk
answering
about
them.
it.
Yeah, so the first one from Abhinav is when you're fanning out for error handling, how do you handle failures at the op level? The fact that each op has two paths forced out our team to split our execution and ETL layers into two separate jobs.
So the question was how we handle failures that happen in that remote execution in a fan out step.
Yeah.
Yeah, so I'm actually going to get into that a little bit here in a moment. But just a sneak preview of that is that we're actually parsing. We have kind of two different signal channels that we can detect failures on. We're parsing the logs as we stream them back from the remote execution to the Dagster layer. And the resource provides this layer that we can parse those logs and detect what types of failures there are, and provides automatic retryability for failures that we know can be retried. And then any like errors that don't fit into a retry category can be percolated up and then fail to run if they need to. Then we also are monitoring any APIs that the platform we're executing on provides us that gives status monitoring as another way to kind of see whether or not sometimes those APIs will report certain failure types that you can't detect in the logs. And so we're also monitoring that at the same time and doing any retrying we need to do there. I hope that answered the question. Maybe things will be a little bit more clear as we get further into the presentation. Were there any other questions?
Yeah, we had one around like how you're doing the execution, but I imagine we're going to cover that here now. So
Yeah, I think that'll fit in really nicely. We'll talk about that in just a moment here. Yeah, is that it for now?
Yeah, I think
Yeah.
that should be good.
Cool.
Cool.
All right. Yeah, so we'll dive into this a little bit deeper and hopefully answer some of those questions a little bit more deeply. So before we do that, let's talk a little bit about some of the goals that we have when we're managing external execution with this infrastructure layer. So the first big goal that we have is minimizing overhead. So when you're spinning up hundreds of clusters or thousands of instances, there's this provisioning time that adds up quite a bit. It's usually 3 to 5, 10 minutes, somewhere in there. That cost adds up a lot as you multiply the number of machines we're adding. So the resources we provide have optimized startup strategies for each cloud platform, and each of these cloud platforms has a different way to get your code up there and get it deployed. So this is another thing that kind of reduces that context overhead for pipeline developers. We also automatically deploy the code that needs to be executed to target environment, which is going to get into, I think, that second question a little bit here. And that makes it so that pipeline operators don't need to build CI/CD pipelines or figure out how to get their code to the target environment. They just write their pipeline, they configure the platform they want to run on, and it works most of the time. And as you can imagine, this is a really big savings in developer time because pipeline developers can stay focused on the domain instead of how they need to integrate with these custom-made cloud systems. It also means that the code can always be tested locally or in CI/CD in the same way it was ran in production. The second major objective here is to be resilient to failures. So our resource layer analyzes pipeline logs and other status indicators to catch transient failures and automatically retry those that are known to be retryable. It also provides intelligent machine type selection to enable us to kind of automatically get instances that are less likely to fail for things like spot failures. The last major goal is observability. So we saw kind of at the operational level how Dagster itself provides a lot of high level observability across the whole pipeline run. But then we also need more low level compute level, like OS level metrics that we want to be able to see. And the resource layer helps us inject those instrumentation agents into our external compute. And then the other major observability dimension that I think doesn't often get enough attention is cost. And so our resource layer helps with that by really helping further our tagging strategy and automatically tagging external resources and kind of allowing Dagster to be our central place that we define tags. And then those tags can be passed on to these external resources. So talking a lot about this stuff, let's kind of dive in a little bit and see how all this works. So here's a high level overview of the architecture that we have involved in running a large scale fan out across multiple platforms. There's a kind of two different stories going on here, so I just want to separate those real quick. So at the bottom here, we have a pipeline for collecting observability metrics from external platforms. I'm going to get into that in a moment. Right now, I want to focus on the top half of the diagram, which shows our external execution flow. So at a high level, the jobs start by either getting submitted through our internal web UI or to the Dagster Plus UI directly. And then from there, it's really the normal flow that Dagster Plus jobs go through if you're deployed on ECS. I'm not going to get into that too much right now because it's well explained in the docs. So yeah, let's dig in a little bit further into what's going to happen in this run worker when we start triggering these external jobs. So just to orient people a little bit, I just wanted to show that that graph that we looked at a moment ago to show what's going on within the Dagster run worker in this context. So in this run worker, we've executed generate batches, and now we're processing a batch, and we've triggered an external execution using the resource that we injected into the process batch of. Now we're going to zoom out a little bit again, staying focused on the Dagster run worker, specifically the fan out op and how it operates. So when the trigger external execution method is called, that's basically what this dotted container is here. The first thing that happens is that we build an external job configuration. So this is taking configuration from the batching op, which took configuration from the run config, and transforms that into the shape that's required by the API that we're submitting a job to. This is also the step where we do any parsing of tags or contextual information that we want to pass along to those external jobs so we get proper cost observability later on. Once we've generated that job configuration, we upload any artifacts that are needed to execute the code remotely on the external platform. So there's a couple pieces that we put together here. So we have the function that the user passes to the resource. We pickle that function, and then we either detect the PyProject TOML and UV lock file that are part of the projects that we're currently executing in, or if the user provides custom dependencies they want to execute on the remote environment, we'll actually generate these mock versions of these files to simplify running this code with UV in the target external execution environment. We zip that up and we ship it to S3, and then we go ahead and launch the external run now that all the pieces are in place for the run to get carried out using that job config that we've built in that first step. That external run hits the cloud API, which kind of kicks off this external compute job. Once we've got that running, we start pulling logs. There's an agreed upon location that this external job is going to write its logs to, and that this run worker is going to pull the logs from. And then at the same time, we're pulling the status of the job from the external cloud API. Different external cloud providers have different APIs for this, so we have to have a slightly different integration depending on the platform we're integrating with. So on the other side of the coin, when this job spins up, we have this entry point, it's this generalized entry point script that our jobs are going to start with when they start on external platforms. Each platform has basically just one entry point that gets shared across all jobs. And what that entry point does is it starts up by initializing instrumentation. We try to do this right away so that we can immediately start getting observability even into this startup script prior to the user code being executed. Once instrumentation is started up, we download those artifacts that were necessary, those environment artifacts, and then we install them into the environment. In certain environments, like in production, depending on the platform, we can skip this step and use Docker containers instead. We do maintain that capability of dynamically installing for local development so that users can make changes locally and not have to go through a CI/CD process or deploy their code. They can just run their Dagster job locally and still have their changes manifest in the remote cloud platform. Either way, whether we're installing the environment dynamically or not, the next step is to execute the user code. And while that user code is executing, we then stream logs back to our object storage, and results are also written to object storage. And that's where the logs get pulled and emitted to the Dagster API or the Dagster console from. Yeah, so that's just kind of a high-level overview of what this resource is doing under the hood. I want to explore a couple of the capabilities that the resource provides beyond just launching and monitoring jobs. So the first of those is the retry flow, which I think gets a little bit into that first question that was asked. So one of the big values that the resource provides is this granular retry strategies. It does this in two main different ways. The first is that it pulls logs that are emitted from our jobs as they're emitted and looks for certain errors that we recognize as being retryable. So In this case, we see that there was an unrecoverable network failure, and we know that this is something that is a transient error that if we retry enough times, it might succeed. And so we can automatically retry this given a configuration that the user provides over here to the job run. Separate class of errors can be detected if the external platform exposes an API that we can pull statuses with. Some of these APIs will report certain failure reasons or types of failures. For instance, the Databricks API will report spot instance interruption failures. So we can use that to indicate that we want to retry those failures when they happen. So when we detect either of those failure types, we evaluate if it's a retriable failure. And then depending on the configuration and the type of failure, we might reevaluate what the configuration is for that external job. And then we resubmit and the process starts again. So I would just want to point out that we have these configurations that can kind of modify or mutate the external job configuration depending on that failure type. So if we have an out of memory failure that we detect, we can actually bump up the memory by provisioning a larger instance type automatically. This kind of retriability is maybe less important when you have just a couple jobs running and you can view the stuff manually. But if you imagine having 500 of these jobs running over the course of a couple of days, it's really, really valuable to be able to keep this pipeline executing at a high throughput by kind of automatically retrying those failures. That allows our pipeline operators to focus on building the next pipeline or kind of isolating the domain-specific bugs that the pipeline might encounter instead of having to kind of figure out if there's 50 errors out of 500 jobs, which are retriable for spot, which are retriable for OOM, and need the configuration adjusted, all that stuff. We try to eliminate a lot of that for operators. So the last capability that I wanted to spend a little bit more time on that our resource provides is cost observability. So the question that comes to mind is basically, where is all the money going? At the scale that we're running at, it's really critical to understand where money is going because efficiency improvements of even 2 to 3% can have really substantial savings. Beyond that, we've found that really deep cost observability during every stage of development and operation really helps developers isolate costly steps and focus their optimization efforts on the places where it really matters instead of just kind of looking, it's not always the case that the longest running step is the most expensive step. It really depends on a whole host of factors. So have you ever wanted to know how much your Dagster runs cost, or can you answer any of these questions? Have you ever wanted to know like how much a specific team spent on Dagster jobs last week? If your jobs don't really take super long or don't use a lot of external resources and your total spend on Dagster infrastructure isn't a whole lot, it might not be super important for you to answer these questions right now. But when you have Dagster jobs that can potentially cost hundreds or thousands of dollars in a single run, these questions get really important. So having a clearly defined tagging strategy is critical to being able to get these kinds of questions answered. Implementing that tagging strategy can be really difficult though. There's a lot of different dimensions that you might want to aggregate your costs across. And manual tagging is extremely error prone and inconsistent, and it's generally just not super realistic to expect users to manually add tags for cost attribution every time they need to launch a run or provision some resources. It's really going to slow people down. They're going to forget. Forcing users to spend time tagging their resources manually also just introduces its own costs in developer time. So beyond that, some of the tagging dimensions aren't even available until runtime, so it's just not possible to manually tag those. So let's dig into kind of how we do this. So many of our workflows provision resources across different cloud vendors. This is kind of one of the biggest challenges we've had to tackle. How do we tag these resources across multiple vendors? You really need consistent tagging across these different resources. And so, for example, if I have a Dagster job whose workers are running in AWS, but it also spins up 2 external GCP VMs, I need to tag all those with the Dagster run ID so that I can get a total cost for this whole job. But if I want to understand just what the cost of a single step is, then I also need to tag the external GCP VMs with their specific step key, which is going to differ from VM to VM. So a lot of different dimensions you got to keep track of here and different places that things need to get tagged. The different things we want to tag with are actually going to be available at different times in the deployment process. So there's 2 different places that things get tagged for us. So we provide static tagging in code using these factory functions. Our users can tag everything within a Dagster definition using a factory function. We call it create Dagster definitions. And then they can provide these enum-based tags to tag everything in that definition. We really like defining our tags in code because it allows us to version control them. And it also, we find that the PR process is a good quality gating exercise where if a user forgets to provide certain tags that we require, it's an easy place to remind them that they need to add those tags. At a lower level, users can override tags that are set on definitions or provide more specific tags with the create Dagster job factory function. Once our jobs are tagged, you can see on the right here an example of what those tags look like. We also create calculated tags from context like the git hash and the git branch. And then if the job is submitted by the UI, we also add additional tags that allow us to attribute costs to the UI users. And then I just want to call out real quick that as a future direction, we're interested in using the defs folder component from the new components framework to set some of these tags without a factory function. The other part of tagging is dynamic runtime tagging. So tagging with values that are only available at runtime. This is a function that we use to parse tags from the Dagster context. This includes things like the Dagster run ID, the step key, asset key, partition key, retry number, stuff parsed from the run config, other contextual elements. This particular function can be used in a lot of different contexts, and we use it within our external execution resource. Here you can see the get Dagster tags call at the start of the execution, the external execution triggering, and then we add those tags to our job configuration when we're creating that external job configuration. Once all those resources are getting tagged appropriately through this external resources, it's kind of passing along those tags to all the different resources we're spinning up. Then the fun part comes into play, and that's collecting all the run metadata from all these different APIs. This is actually where most of the work is, since every platform provides cost or usage information in a different way, usually with different terminology and different cadences. Some platforms are going to export CSVs, some expose usage through REST API, some is GraphQL. GCP does BigQuery tables. So we have all these different pipelines to pull down that information and normalize it and transform it and clean it up. Luckily, one of my coworkers handles that. Thanks, Ryan. And all the output of his hard work and transformations is a set of dashboards that users can look at to understand their Dagster costs. These pipelines usually manifest as time partitioned assets for us. So some of them are hourly partitioned assets, some of them are daily partitioned assets. We find this abstraction to be a really nice way to represent these, as it allows us to backfill stuff really easily when things change or things fail. So we've really enjoyed the time partitioning in this particular use case. Getting a high level picture of costs in the sprawling cloud environment is really difficult. It's hard to know where to start sometimes, but if you're looking to try and figure it out, I'd suggest you start by trying to answer a single question, like how much does our daily study ingestion pipeline cost us each month? From there, you can follow your data flow to see what all resources need to be tagged and what layers you have to automate that tagging as much as possible. Automating tagging for us in cost observability has been a huge success. It's really enabled our teams and developers to have empirical evidence to guide their optimizations and investigations. It makes it really easy to measure cost performance during integration testing and to make sure that a certain change doesn't result in unexpected costs. Our internal drug discovery scientists utilize our cost observability as well. This gives them the ability to understand how much query they're running costs and allows them to prioritize their research questions and methods. It's also spurred collaboration when a scientist has found out that a particular analysis costs a lot of money. It's enabled them to dig in with our pipeline developers and refactor or rework pipelines so that they're using a different method that the pipeline developer might not have known was possible. It's based on the domain and results in a much cheaper pipeline. So cost observability has been a huge success. It's pretty impressive how much money you can save once you know where your money is going in the first place. Just to summarize, Dagster has really helped us at Empirico operate at a scale in a lot of different ways. We've seen how observability and resiliency are really critical at scale, and how the transparent infrastructure layers that Dagster gives us can support those requirements. We've also seen how Dagster as a control plane significantly reduces context overload, which improves our developer efficiency greatly. Just to touch on some quick future directions, we're interested in looking more into Dagster components for abstracting the fan-out assets and also for tagging and secrets retrieval. We're looking into tighter integrations with Ray because that can do a lot of the environment spin up and remote execution that we talked about kind of automatically for us. And then we're also looking to move some of our logic into a custom executor instead of resources. And then I'll wrap up just with a quick thanks from Colton and Alex for helping me put this together, Nick Schrock and the rest of the Dagster team, the data infrastructure team and data engineering department at Empirico, and then the rest of the Dagster community, especially Georg, Daniel, Brendan, Steven, everybody else who contributes their time to the community. Thanks a lot for being a part of it. And then just some links that you guys can check out later if you want to further your reading a little bit.
Nice. Maybe you can leave the links up while we answer some questions.
Yeah.
If you can go back into presenter mode. Yeah, cool. Nice. Thanks so much, Zach. There are a few questions, and we have around 10 minutes to address them. So I think we still have some time. I think a good question here is, why did you go the resource route for these external executions versus kind of like a custom executor or something along those lines, or a custom runner?
Yeah, that's a great question. I think there's kind of probably two main reasons we went the resource route. The first was that it's a little bit more flexible for us in terms of being able to be injected in like any other pipeline type. So if we wanted to implement an executor, then we would have needed to include the functionality that any other executor that we wanted to emulate could perform. So I guess another way of putting this is, if we implemented our own executor, then we wouldn't be able to, in some cases, use the ECS executor unless we wanted to add that ECS executor as a like sub functionality within this executor this custom executor. So by keeping it as a resource, we can inject that resource into pipelines that are using the multi-process executor, or into pipelines that use the ECS executor or a different executor. So it allows us to stay a little more flexible to other executor use cases. That being said, long term, I think moving in that direction to kind of finding the set of executor functionalities we want to provide and kind of combining those with probably a tag-based strategy where each step is able to use a different executor functionality based on a tag that's assigned to the op. That's kind of a architecture I've had in the back of my mind for some time. It just obviously has some complexities involved, but I think that would kind of be like the ultimate way to present some of the stuff. So yeah, that's a great question though.
Cool. And I actually have a question of my own that I'd like to ask really quick. When you're talking about like the cost savings, you're able to allocate different memory or CPU resources for each execution. How are you determining like whether or not you are like saturating that execution, like 100% memory or not utilizing it enough? Is that the dashboard that you said your coworker was working on just to see like resource allocation and usage?
Yeah, great question. So resource allocation is so the pipelines I was talking about at the end are generally a little bit more focused on cost observability specifically, kind of at the run level usually, sometimes at the row level. In terms of more CPU memory performance metrics, we that's where the instrumentation agents that we inject come into play. So we inject an agent that does open telemetry collection onto our remote execution compute instances, and then those go to dynamic dashboards that they kind of automatically group instances by Dagster run ID or step key or that type of thing. And then users can go to that set of dashboards, these performance dashboards, to see what CPU or memory or IO usage is like across all the instances involved in their Dagster job. Those dashboards can be really impressive sometimes when you've got like 500 instances in a run and you can see a high level view of like color-coded CPU metrics across all the 500 instances. It's pretty cool.
Yeah, that's super cool. Nice. Alex, do you want to talk about some of these Q&As?
Yeah, we got another question from Abhinav. Given this architecture, it seems like you will have a lot of parallel graphs running all at once, and it also seems like you have a huge asset graphs. What are some of the scaling challenges that you've had with the Dagster platform itself, and how have you worked around this? For us in particular, we've had some trouble with the event logs overwhelming our DB, and we've also had some trouble with the UI for massive dynamic graphs. For our time partitioned assets, we've needed a custom way to enforce data TTL, as too many partitions will also overwhelm the UI and plotting interface. All problems I think you guys should have are solved, smiley face. But Zach, if you could talk through some of the scaling challenges you guys have had.
Yeah, that's a great question. Definitely experienced some of these challenges. I will preface the question by we have a little bit of a cheat code in that we're using Dagster Plus for most of the stuff, and so the Dagster, a lot of these challenges have shown up in the Dagster Plus platform over the years, particularly like the event log, as it manifests in the UI. At one time, we had a lot of challenges with when we emitted enough logs to Dagster, even through Dagster Plus, the UI would start crashing and just be totally unresponsive for runs. The Dagster team has done an amazing job over the last couple of years in terms of scaling that platform to be able to kind of handle up pretty much everything we can throw at it these days. For partitions, time-based partitioned assets, and how that can overwhelm the UI. That's one reason that we tend to really only use partitioned assets for specific use cases like hourly or daily partitions, where we don't really end up with usually thousands and thousands of partitions that are going to overwhelm the UI. But yeah, so I say it's a little bit of a cop out, but in large part, how we avoid these issues is using Dagster Plus and just relying on their platform team to take on the challenge of making this UI scale. I wish I had a little bit better answer for you in terms of how to handle this at the OSS level, but that's how it is.
Yeah, and then I had one of my own questions actually. When you're thinking about how you do like sampling when you're running these like big jobs, are there any like special sampling strategies that you or your scientists leverage to get the most out of these massive data sets without like running the whole thing?
Yeah, great question. It's something that we've been exploring more of because obviously the scale is so big, you can't run analyses these big quite like all the time. But part of why these analyses are so big is so that we can kind of generate a smaller condensed. It's kind of a big funnel, so that we can generate a smaller condensed version, more or less, of these data sets that our scientists can query. We do use sampling a little bit more at the like testing stage. I can't say if there's like really necessarily like very sophisticated strategies for sampling, but our bioinformaticians use a lot of domain expertise to kind of identify certain entities of the data or dimensions of the data that are representative of different type like trends you'll see in the data sets. So like there might be certain genetic variants that are underrepresented in the data set or overrepresented in the data set. And they want to be able to, they'll subsample the data set for both those different representations and then evaluate how that model performs on those different representations so that they can understand whether the model is overrepresenting things or underrepresenting things given the sample size that's being introduced. So I don't have like a super straight answer to your question, but it is something that our bioinformaticians spend a lot of time thinking about, is how to test subsamples of the data in a way that's representative of the analysis we're trying to perform.
I think Thanks, Zach. I think that we don't have too much time, but I think that leads nicely into one final question I have around this like local to production developer experience. So you mentioned these scientists being able to like operate on these samples of data. Um, but you also have all these limitations in like how you can retrieve data from different APIs and all these different environments. How are you able to kind of like emulate this environment for them to be able to do their work? Are they essentially like working in isolation on these scripts, like kind of like defined with like the entry point that you were talking about? And then you're productionizing that, or are these scientists also kind of like working within the Dagster environment but locally as well?
Uh, it's more so the latter. So one of the things that's been really cool about this architecture we've come up with is that there's very little visual or functional differences between running a pipeline locally on your machine versus running it in Dagster Cloud or just in the cloud in general. So that's been really valuable because, and actually we've had to explicitly tell people like, hey, if you're going to run a analysis that is important, you need to not run it on your local machine, because your local development environment that we create is capable of running these jobs on the remote cloud platform that we need to interact with. So people use this in an ad hoc manner to just do like quick testing when they want to interact with that external platform. But then it's also possible to run, a whole large scale analysis from your laptop if you wanted to. We don't encourage that because we want to get all that operational metadata in the cloud. It sucks to run something on your laptop and then not be able to link it to somebody. So yeah, I guess to long story short is that we really try to minimize that difference between local development and cloud and production environments. Sometimes a little bit to a fault, but we found that it really improves developer efficiency, and then it also means that my team doesn't really need to be involved in someone wanting to take an idea from local development to production. We have the tools published, and they just use them and push their code to production when they go through the deployment process, and then they can run them. So it's been really, really valuable.
Nice. Cool. Well, I think that's it for the questions. But I just want to thank you again for joining us for this webinar.